Okay, good morning. So today we're going to be talking about scattering at hadron colliders. And so just by way of review, we've calculated now two different what are called parton level cross sections. So parton level. And from now on, parton level means that I'm going to put a hat on it so that we know it's parton level. And so the cross section, the differential cross section with respect to a Mandelstam variable for scattering of two different quarks off each other, we worked out was 4 pi alpha s squared over 9 times s squared plus u squared over t squared. Okay, but I promised to put a hat, so I'm going to put a hat on the sigma. I'm going to put a hat on all of our Mandelstam variables. Okay, we'll mention in a little bit why the hat. So we worked that one out, and then we worked out, or I didn't work it out, but I quoted the answer for you for gluon-gluon scattering. So if I have gluon-gluon goes to gluon-gluon, right, then that turned out to be 9 pi alpha strong squared over 4 Mandelstam s squared. And then there was u squared plus t squared over s squared plus s squared plus u squared over t squared plus s squared plus t squared over u squared plus 3. Okay, so suppose we now scatter, for example, a proton off an antiproton. So suppose we scatter a proton and antiproton, and we get out some hadrons. Or we could do this. We could scatter two protons together and get hadrons. But either way, these protons and the hadrons contain gluons and quarks in them. So this happened at the tevatron at square root of s was 101.96 TeV, and at the Large Hadron Collider at up to 14 TeV. They haven't actually got quite up to 14 TeV yet, but that's the plan. And notice there are no hats on those square root of s's. So the reason is because the hadrons and the protons are composed out of gluons and quarks. And so the microscopic thing that's going on is this scattering. But those are called partons, and they're different, and they're only parts of the proton and antiproton or proton-proton. Okay, so what one observes is not the parton level thing. What one observes is, for example, proton-proton goes to jet of hadrons plus another jet of hadrons plus anything. And I'll use X for anything. So what we do is we think of this as factoring. And people have done a lot of arguing about how good is this assumption of factoring. So we think of the event as factoring into two parts. Okay, and so the first part is the hard scattering, which means the partons. Okay, so of point-like partons. And so those are the things that we've already calculated. Things like quark prime goes to quark prime. So we did that for Q equals up and D prime equals down, but it could be for any two different quarks. The prime just means different. So I could also do two same quarks, which will have more Feynman diagrams and therefore a different cross section. Or I could do quark scattering with gluon. There's some Feynman diagrams for that. Or I could do quark anti-quark goes to, for example, a different quark and a still different anti-quark. The primes just mean different. Okay, or I can do gluon goes to gluon. Or, for example, quark anti-quark goes to gluon. There are many, many of these. You can even have things like quark anti-quark goes to quark anti-quark plus gluon. That's a 3-body final state. And the list of these is essentially infinite. So you have to divide this into the things that you think are important and the things that you think are not important. Probably, well, actually, all of these are probably going to be important, but say something with quark anti-quark goes to 17 quarks and 17 anti-quarks will probably be less important. So when you do this calculation, one thing that's nice is that asymptotic freedom, the fact that the perturbative renormalized coupling gets small at high energies, says that the calculated cross sections, and remember I'm putting a hat on them to say that they're parton cross sections, are more reliable at higher energies. So the higher in energy we go, the better our calculations become. So you should think of hard scattering as being fast and small. And that's just because the time scale, for example, or the distance scale is much, much less than 1 over lambda QCD. That's the scale at which the QCD coupling is actually blowing up, and none of our calculations make any sense. Okay, so that's hard scattering. And then the other part of the process that we're trying to calculate is soft, which you should think of as slow. These are QCD processes at low energy. And so what do they consist of? They consist of things like initial and final state radiation of extra gluons. Okay, and then what's known as showering and hadronization. Into color singlet bound states. So let's say, for example, let's just say I produce in one of my things, I produce a quark here. That quark has to be in a bound state eventually. It has to form a bound state because the QCD coupling at large distances starts to blow up. And so it will do so by emitting more gluons and more quark anti-quark pairs, and they will sort of combine in some very complicated thing, some very complicated process that's soft and slow, which we pretty much have no chance of actually calculating in any sort of meaningful way. So the important thing is just going to be that we're going to calculate the hard scattering part, and then we're going to sort of use computers to get some estimate of the soft and slow part. The dividing line between these, because there's always some dividing line between what's a hard scattering process and what's a soft process, is called the factorization scale. And I think it's traditionally called Q. Okay, and it's some quantity of units of mass or energy or time or distance. And if you're smaller than that, then it's a hard scatter. It's considered part of the hard scattering. And if you're larger than that, it's considered part of the soft process. So somehow we have to put these two things together. And so the parton level things, these are these ones that we can actually calculate. And so one way to do that is, let me just write down the problem here. How can we get observable cross sections? That means things that actually correspond to numbers that we can measure from parton level ones, which are the ones we can actually calculate. So one thing we need to know is we need to know how many partons of a given type there are in a proton. So how many partons of a given type? That means quark, antiquark, or gluon. And for each quark or antiquark, also what flavor it is. Is it up or down or strange or so on? So of a given type, and energy, for that matter, are present in each proton that we're scattering, or antiproton. Okay, so what we're going to assume, because for the Large Hadron Collider and even for the Tevatron, this is a very good assumption, is that the square root of S, that's the characteristic energy, is much, much larger than the masses of the partons. So of partons. And so basically we can pretend these things are massless. The partons are massless and they're going at the speed of light. So for example, for each hadron, if it's really relativistic, for each hadron H, the 4 momentum P mu of H is just the time component is the energy. And if it's moving in the Z direction, it just looks like that. We're neglecting the mass. The energy is much, much larger than the mass of the proton. Okay, so usually the hadron is either a proton or an antiproton. And so this is hopefully a good assumption. And then we say for each parton within the proton, so we'll call the partons A, within the hadron, the proton or antiproton. So the partons again could be gluon, up, down, strange, charm, up bar, down bar, strange bar, charm bar. You might think it's funny that we're including charms here because charms are heavier than protons, but nevertheless, it turns out there's some probability amplitude to find a charm quark within a proton. Only for a short period of time, but that's enough to make it scatter. And sometimes you even include the bottom and the antibottom, even though they're much heavier than a proton. There's still some non-zero probability to find one within the proton. So for each one of those partons, we can also write down its 4 momentum, Pa mu. And the idea is it's some fraction of the total 4 momentum of the hadron. And that fraction is traditionally called x. Okay, so we're just saying the parton momentum is proportional to the hadron momentum that it's part of. And X is sometimes called Feynman's X. Or sometimes it's called the momentum fraction of the parton. Okay, so now to make progress, we make a definition. We define the following thing called a parton distribution function. This is the original PDF. In fact, there's more than one of them. These are PDFs, and they're defined by the following thing. So I'm going to say in big parentheses, the probability of finding a parton of type A with 4 momentum equal to, or 4 momentum between, let's say, x times p mu for the hadron and x plus dx, a differential, times p mu, inside a hadron with momentum p mu. Okay, so that's some big probability that we could, in principle, either measure or calculate. And we're just going to give it a name. We're going to call it F. It depends on what hadron we're talking about. It depends on which parton we're asking about. And it depends on the momentum fraction that we're asking about. And then if we're asking for what it is between x p mu and x plus a little bit p mu, it's going to be proportional to that dx. Okay, so that's the definition of a parton distribution function. The probability of finding a given parton of a given type within a hadron of a given type with a certain fraction of the momentum. Now, actually, this, I've written it as if it only depends on x, but it actually depends on the factorization scale too. So actually depends on Q. Q is the dividing line between what's a hard scattering event and what's a soft event. And so basically, if you allow the parton to have a higher or a lower energy, that's going to affect what probability you assign to it. So for example, suppose we're indeed talking about a proton, which is the most common case. So a proton, we remember, has valence quarks that are up, up, and down. So naively, you might think that the probability of finding an up quark is twice as much as finding a down quark. But that we'll see is not exactly true. In any case, what we need is we want inside the proton, what's the probability of finding an up quark with a fraction of the momentum x? And what's the probability of finding a down quark with the fraction of the momentum x? Okay, but we also need for gluons. There's some probability that if you look inside a proton, you'll see a gluon. So there's a parton distribution function for the gluon inside the proton, which also depends on x. And there are also virtual quark and anti-quark pairs. So it's not just up and down. There is also some probability within the proton of finding an up bar, for example, which depends on the fraction of the energy, and a down bar, and a strange, and a strange bar, an anti-strange, and even for the charms. but I think I'll stop there. So let's say you knew these functions for the proton, then just for the antiproton, you would also know them because protons and antiprotons are just related by changing every particle into an antiparticle. So given the PDFs for the proton, those for the antiproton follow. Okay, so what does that mean? That means the parton distribution function for an antiproton and a gluon is actually exactly equal to the parton distribution function for a proton to find a gluon. And so for that reason, it's very common to just write a shorthand notation and just call this G of X. They're the same thing anyway, so why not give them a single name? And then the parton distribution function in the proton for an up quark is the same thing as the parton distribution function in the antiproton for an anti-up. And so that's just traditionally called U of X. So if you see U of X, that's the parton distribution function to find an up quark within the proton. And similarly for downs. Okay, so this is a true statement. This is the down quark PDF. And then you could ask, for example, for a proton, what's the probability to find a U bar? That's the same as in an antiproton to find a U quark. And that's called the U bar of X parton distribution function. Okay, so note that certainly it is not true that they're equal. U of X is not the same as U bar of X. Okay, and as I said, these all depend on the factorization scale. And so we should really write, instead of just, for example, G of X, we should write G of X and Q. We choose some factorization scale, and same for U, and same for U bar, and same for D, and et cetera. Okay, so there's this factorization scale, and there's also a renormalization scale that goes along with the couplings, and it's a very common thing to set them equal. So you set the factorization scale, which we call Q, equal to the renormalization scale for the couplings in the theory. Which is mu, that's what we called it. In fact, some people call one mu and the other one q. There's no actual consensus on this of which one is q and which one is mu. But often we're just setting q equals mu anyway. So in principle, in a perfect world, which we do not live in, observables shouldn't actually depend on either one of them. So observables don't depend on mu or q. And the reason is because for the renormalization scale, remember, that was something that we chose arbitrarily in the hopes that it would make perturbation theory converge faster. But other than that, it's arbitrary. We could change it by a little bit, and anything that you can actually measure shouldn't depend on our arbitrary choice. And the same thing for q. Q is sort of an artificial dividing line that we put between hard scattering and soft events, soft processes. And where we put that is up to us. So it's an arbitrary human choice. And physics things shouldn't depend on arbitrary human choices. Okay, but in practice, if you actually calculate, you'll find out that if you truncate your calculation at fixed order in perturbation theory, which we always do, because nobody knows how to sum up all orders in perturbation theory, then your answer will depend on these. And so the dependence gives you a check. A check is that the calculated dependence, as opposed to the actual dependence, should be mild. Okay, and if it's not mild, then that's usually a sign that you haven't calculated enough terms in perturbation theory, or a sign that perturbation theory is just not converging. Okay, any questions so far on parton distribution functions, how they're defined? All right, so one thing they do is they satisfy some rules that are useful. So some rules for PDFs. And so one sum rule is the following. Let me write it down and then I can explain what it means. If I integrate over all possible values of x, the momentum fraction, meaning between 0 and 1, and I do the up quark PDF minus the up bar PDF, that should be equal to 2. So all that's saying is that the net total of the proton has 2 up quarks. The net total meaning I'm integrating over all possible fractions of the momentum that it could possibly have. And basically I can have up bars, but the only way to have an up bar quark in the proton is it comes with a virtual up quark along with it. And so if I subtract that off, then I should get the 2 that tells me there are a net 2 up quarks in the proton. Okay, and so by the same reasoning, if I do the same thing for down quark PDFs and anti-down, that should be 1, okay, for the proton. And similarly, if I do it for the strange quark PDF minus the anti-strange, okay, that's 0. That's just saying there's no net strange quark content in the proton. It's 2 ups and a down. In fact, even before you integrate, they're equal to a very good approximation. They're not exactly equal, but S of X is very close to S bar of X. So to a good approximation. In fact, the only reason it's not exactly true is because of some effects in the weak interactions, which are very small for this. Okay, here's another sum rule. Maybe they should actually be called integral rules, but they're called sum rules historically. Is if you sum all proton 4 momenta contributions, then you should get P mu, which is the total 4 momentum. So how does that look in terms of parton distribution functions? Let's integrate from 0 to 1. We're integrating over all momentum fractions of the momentum fraction multiplied by the probability to have some parton with that momentum fraction. So there's some probability to have an up, there's some probability to have an up bar, there's some probability to have a down, there's some probability of a down bar, and we add just all of these things up. S bar and S. And let me not forget the gluon one. There's no anti-gluon. Gluons and anti-gluons are the same thing, so I just include the gluon once. All of that is equal to 1. That's just saying I add up all the momenta for all the partons in a proton, I get the total momentum of the proton. Okay, so here's a very naive and very wrong estimate of a PDF. You might say, and I'm going to write U naive for this. The naive thing to do would be to say, if I have up, up, and down, and they share the momentum equally, then I should just get U naive equals 2 times delta of x minus 1/3. That would say each up quark carries exactly 1/3 of the proton momentum, and there are 2 of them, right? And then D naive of x would be the 1 down quark carries exactly 1/3 of the 4 momentum. And naively, then everything else gets nothing. So the only reason I'm writing this down is to remark, so these would all be 0 according to this naive prescription. And the only reason I'm writing this down is just to emphasize how completely wrong this is. Okay, the actual values of the parton distribution functions look nothing like equal sharing of the momenta into 3 parts. So what do they look like? You can't solve for them. Nobody knows how. But it's often nice to know that you can't solve for something, because that relieves you of the responsibility of trying to solve for them. So I should say, instead of them, can't solve for PDFs from theory, although there are now lately been some valiant attempts by people doing lattice quantum chromodynamics to try, and maybe they're even making some progress. But the best way by far is to just infer them from other experiments. So infer from experiments. And there are people who spend their entire lives doing this. I'm going to write down a few of the collaborations that do this. One is known as CTEC. So this stands for Coordinated Theory Experiment for QCD. And I think they've lately taken to just calling themselves CT. Okay, but it's a group of people whose main job it is to figure out what the parton distribution functions are. And then there was another one. It used to be called MRST, which was Martin, Roberts, Sterling. It was just, it was a few people. Can't spell that Sterling today. And Thorne. But then I think Thorne retired, and it became, for a while, MMHT. And actually, I haven't looked lately to what they call themselves lately. There was GRV, which was Gluck, Rea, and Voigt. And I think this one is old. I don't think they maintain this anymore. One that's more recent is called neural network PDFs. They use neural networks to estimate them. Okay, this is more recent. Okay, and so if you're doing some calculation, you can try it with one PDF and then hopefully try it with somebody else's PDF and hopefully get the same answer or close to the same answer. Of course, you won't get exactly the same answer because they're not quite the same. They use different methods to fit experiment to get the parton distribution functions. So one thing they all do is you can divide, for example, the up quark and the down quark PDFs into 2 parts, what's called a valence part and a virtual or C part. Okay, so the way that works is the total up quark PDF is a valence part plus a C part. The S here is not to be, that's for C, not strange. And the C part is defined to be the same thing as the up bar PDF. So what is this saying? This is saying the probability to find an up quark is the same thing as the probability to find an up bar, if there's a virtual up-up bar pair, plus some extra part that's accounting for the fact that the proton has a net number of up quarks. Okay, and then the same for the down quark. There's a valence part of the PDF and a C part, and the C part of the PDF is the same as the probability to find a down bar. Okay, so now you can make graphs of these things. So let me make a graph. I'm going to attempt to sketch as a function of x. So x goes from 0 to 1. And so in the middle here is 0.5. And then you can put, what's usually graphed is not the PDF itself, but x times the PDF. So x times the PDF function. And so if you do this for example, the up quark, it has a shape that looks something like this. Okay, so the probability that a single up quark is going to carry most of the proton's momentum is non-zero, but extremely small. But its probability to have a very small fraction of the momentum is pretty large. Okay, and then this divides into a valence part, which is actually responsible for the bump, and then a C part, so this is the valence, and then a C part, which is mostly at small momentum fraction. Okay, and the C part is also known as U bar of X. Okay, so this is just a gross sketch. In reality, way up here at high momentum fraction, it goes to 0 really fast, faster than I attempted to draw there. Okay, but then you could do the same thing for, this is all for up quarks. And I could do the same thing for down. So I guess I should have called it, I should have called this U of X. So this is going to be X times D of X as a function of X from 0 to 1. And so one thing is for downs, the probability to find a down is just generally smaller. So it's going to look something like this, right? Because there's a more net up quarks. And then the valence part of it is responsible for that bump. And then the C part of it is responsible for the fact that you have a very good chance of finding a virtual down quark or anti-down but if it's virtual, it probably carries a very small fraction of the momentum. Okay, and then you can do for the gluon, as a function of X, this is going to be X times the gluon PDF. These are all for some fixed value of Q because I'm just sketching anyway. And so for the gluon, it looks something like this. It's just very large at small momentum fraction, and then it goes to 0 at large momentum fraction. So I should have probably put 1 here and 0.5. Okay, and then for strange and anti-strange, it's also, well, it's even smaller. So this would be S of X. And then for charm, it would be really small because charms are more massive, so it costs more energy to make a virtual pair of them. And you can even talk about the probability to get a virtual bottom anti-bottom pair, which is very small indeed. Okay, so that's roughly what they look like. These all depend on Q. I've just shown them, I've just attempted to sketch them for one value of Q. But also when you ask, for example, you go to CTEC and say, give me your PDFs, they'll say, which one? So there are different sets depending on exactly what sort of thing you're going to use them for. So there are different sets for LO means leading order. So if you ask them, they'll say, did you do a leading order calculation or did you include loop corrections? If you only did leading order, you should use this set. If you included next to leading order, which means loop corrections, then you should use this set instead. Although there's also a paper by somebody who claims that you should always use NLO, even if you did leading order. And I actually found that paper to be kind of compelling. The people who said you should just ignore the leading order ones and always use next to leading order. Okay, and then there's a different one that you use if you're doing deep inelastic scattering, which is something you use with fixed target experiments. So you just have to be aware that there are, even within different collaborations, there are different sets of PDFs and different queues that you use. So a general feature is, suppose you're going at larger Q. Larger Q tends to mean that gluon and C are more important, relatively speaking. But again, in principle, it shouldn't matter what you use, as long as you include as long as you're calculating a high enough order in perturbation theory. Okay, so now suppose we're doing proton-proton or anti-proton scattering. I'll just refer to them as hadrons. Consider two hadrons, H and H prime, containing partons. I'm going to call them little a and little b instead of capital A this time. I don't know why. And suppose, as we've seen, you've calculated or you somehow know the differential cross-section for the parton process. So there are the two partons. They might be quarks or they might be gluons. And they scatter to give something else. And you know that differential cross-section, which carries a hat because it's the parton level thing. So suppose this is known. Okay, and X is just some relevant final state. Maybe it's a top quark, anti-top quark pair. Maybe it's a Higgs boson. Maybe it's something else. Okay, so then the cartoon that we draw that tells us how to use PDFs is the following thing. Over here, I'm going to draw one of my hadrons. Hadron H. And so it contains a bunch of partons. Okay. It contains also a 4 momentum P mu H. So out of that, we're going to select one of the partons. And so we need a parton PDF. And the other ones are just spectators. We ignore them. They're part of the soft process. So now we've selected one of the hadrons, or sorry, one of the partons, and that's going to participate in our hard scattering differential cross-section. So we know its momentum. It's x sub a, the momentum fraction, times pH mu. On the other side, so over here, I'm going to draw the other hadron. So hadron H prime. Okay, and it's got some PDF. And we're going to select it to participate in this process. So this is parton B. We're going to have to sum over all these partons later. And then the rest of them are spectators. Okay, and then in our hard scattering event, out comes some final state particles. Let's say K1 and K2 for our d sigma hat. Okay, and so the parton level process has some Mandelstam variables. Okay, so there's S hat, which is parton A plus parton B squared, T hat, which is going to be parton A momentum minus parton K1 momentum squared. Same for U hat. Okay, and in the for the hadrons, it's going to be, if we work in the center of momentum frame, pH mu, as I mentioned before, is E00E. pH prime is moving in the opposite direction. So that's going to be E00 minus E. Okay, and so from these, the hadron, or the unhatted S, is pH plus pH prime squared, which is just 4E squared, because it's 2E squared. Okay, so now PA mu is the momentum fraction XA times E00E, and parton B has its momentum fraction times its hadron's parent momentum, E00 minus E. So in terms of that, we can calculate what's S hat. S hat is, it turns out, XA plus XB squared E squared minus XA minus XB squared E squared. Okay, and that's just, when you turn the crank, 4XA XB times E squared. In other words, that's the total S times the product of the four momenta fractions, XA times XB. So the moral of the story is, at the Large Hadron Collider, S might be 13 TeV, but S hat is less. In fact, it depends on just the product of the fractions carried by the different partons. Okay, so we're now ready to take this cartoon and this information about the kinematics, all here, and turn it into an actual formula. So let me write down the formula. The total cross-section to have hadron H and H prime goes to X is the following. So first of all, you sum over all the partons that could contribute. For each one of those parton types, you integrate over all the possible momentum fractions that it could have. So I'm integrating both over XA and XB from 0 to 1. And then for each one of those, I put in the probability that I actually had a parton with that momentum fraction. And then finally, I put in the differential cross-section for the hard scattering parton event. Okay, and these are the things that we sort of had for two different examples, but there are many other examples. These are functions of S hat, T hat, and U hat with, for example, PA hat equals XA P hadron, etc. Okay, so that's what you have to do to actually get a number out. Next time, we'll talk about some examples of doing this in practice, but basically you need to find or calculate a lot of parton level differential cross sections. You need to get a computer program that's going to give you the parton distribution functions. So they used to give them as fitted functions of a given form, but now they just give it as a big table of values, and you have to interpolate to get the actual parton distribution functions. Then you have to numerically integrate over the momentum fractions, and you're summing over all the different partons that can contribute. And then finally, you get out a cross-section that you can actually compare to experiment. Okay, so this is compared to experiment. And either verify that things are working the way they should, or hopefully, which hasn't happened much yet, discover a new particle. All right, any questions on that? Okay, so next time, as I said, we'll talk about different examples. You'll get to do an example or two for homework of just writing down the formula. We're not actually going to compute things numerically because I can't expect you to write programs involving the PDFs, but just write formulas that tell you how to calculate this given all of that stuff. Okay, so we'll do that. You have homework that's due on Monday. Unfortunately, I'm going to be doing a little bit of traveling starting this afternoon. And so I won't, as usual, be able to have Zoom sessions if people have questions, but I can probably try to answer questions by email rather than Zoom. And if you have a question before about 2:30 this afternoon, I can also try to Zoom on that. All right, any questions for now? All right, so if not, I will see you on Monday virtually. Have a good weekend.
Thanks. Have a good one.